So we were just doing the Shatler principle last time. Okay, so I told you there's reversible reactions. Reaction happens in forward and backward. Equilibrium is when the rate of forward reaction equals the rate of backward reaction, specifically rate. If you increase temperature, equilibrium would favor one of the reactions over the other one, which is that it would favor the endothermic reaction. If you decrease temperature, equilibrium would go on to favor the exothermic reaction. So we showed you, I mean, if you, like in this water example, if you increase temperature, more evaporation. If you decrease temperature, there's going to be more condensation. So whenever you alter the conditions, the equilibrium is going to be affected. One of the reactions would be happening faster compared to the other one. Then we talked about pressure. We talked about pressure, that if you increase pressure, you're compressing it. The volume would decrease. There's going to be less gas moles, less gas produced. Less gas mole side would be favored. Yani is piston ko, if you start pressing it down, there wouldn't be any room for gas. There's going to be less gas produced. Vice versa, if you decrease pressure, you're basically pulling the piston upwards. The volume increases and there's going to be more gas that's going to be formed. And remember, pressure would only affect gases. So if an equilibrium doesn't have gases to begin with, pressure is not going to have, it's not going to have any effect at all. So the equilibrium must have gases involved. Otherwise, this thing will have absolutely no effect. The last thing is, the third one is, so the third point is about concentration. And remember, it's specifically, it's not about quantity even, it's mainly about concentration. So if you decrease concentration, yeah, if concentration is increased, or decreased, both ways, of reactants or products, any one. So if concentration is increased or decreased of reactants or products, then the equilibrium would try to do the opposite. Would try and do the opposite. And it's going to be the exact opposite, that it's going to try and do. What that means is that if you try to increase concentration of anything, and remember, keep this in mind, we're talking about concentration. So if you try to increase concentration, what would the equilibrium do? Equilibrium would try to decrease the concentration, and vice versa. As equilibrium would try to decrease the concentration, and vice versa. So I explain what's going on. What's going on is that if you have a container, I mean, the same equilibrium, let's talk about the same equilibrium. There's liquid water, and that liquid water is turning into, so you got H2O liquid, and that H2O liquid is constantly evaporating to form H2O gas, and vice versa. So there's this equilibrium that's happening. Both things getting formed. So the rate of forward reaction, the rate of backward reaction is kind of equal. So let's say there are lots and lots of liquid. Water molecules, lots of them floating around. So lots of them floating around. So what is this? What is meant by this statement? So the statement is, if you try to increase or decrease concentration, let's say I try to decrease concentration of one of the things. So let's say I go in and I remove all water vapors. So I went in and I removed all the water vapors. They're gone. So what will the equilibrium do? Now, all of a sudden, one of the reactions has stopped. Which one? It's the backward reaction. I mean, condensation is no longer going to happen. Remember, I made this change. I introduced this change into the system. It was fine. It was in equilibrium. I went in and I removed all the water vapors. So all the water vapors are all of a sudden gone. What would the equilibrium do? The equilibrium would immediately stop the backward reaction, because it's not possible. It can't happen at the moment because there is no water vapors. So this condensation is out of the question. No condensation would happen. But evaporation would still go on. So what would happen now? More water vapors are going to be automatically formed because evaporation would still go on. I remove water vapors, evaporation happens and more water molecules are formed. So it's trying to do the opposite. I continuously remove water vapors, it does exactly the opposite. So I remove water vapors, it produces more water vapors. So is this point clear? That it does the exact opposite. Also, is this clear? Mahad, Sidra, is this clear? Amna, is this clear? So it's going to do the exact opposite. And if I try to increase water vapors, let's say I open the container and I add, well, what I did was I added a lot of water vapors. It will automatically, because there's so many water vapors, that the condensation would automatically speed up. And the huge quantity of water vapors that I've added, they would automatically start turning into liquid water. The speed of condensation would automatically increase. So what I did was I tried to increase water vapors by adding more of them from outside, but all of a sudden the condensation sped up. It started happening at a faster rate because you had so many water vapors that they started condensing at a much faster rate. And the amount of water vapor would automatically decrease again. So the point is, whatever happens, whatever you try to do, it's going to do the exact opposite. So that's your third point. And I'm going to talk about this concentration thing. Okay, let's talk about this. Remember, this statement is only true for concentration. So remember, solids, whenever you see a solid or liquid, their concentration never changes. So their concentration does not change. Because you have to understand what concentration is. Concentration, the term concentration only applies to aqueous solutions. I mean, you always heard about concentration. So the term concentration only applies to aqueous solutions or to gases. I mean, this is a very important point. or gases. So what is concentration? I mean, you've all heard about it. Concentration is a term that describes the spacing of the molecules. Now that spacing can change in gases, because in gases the particles are all flying around. So that's like one container that has gas molecules, and here's another container that has gas molecules. But one of them will have lesser spacing because one of them is more concentrated. Because concentration is the amount of particles per unit volume. So that kind of describes how close together or how far apart the particles are. So this one is obviously more concentrated. So remember, from now on, I mean, although you're all pretty good with this probably, you can tell which one is more concentrated. This one is obviously more concentrated, but from now on, think of it as the spacing between particles, because if things are less concentrated, they would be very far away from each other. If things, I mean, this is a gas that is less concentrated. If things are more concentrated, they would be a lot closer to each other. And the same term, concentration, also applies to solutions. In solutions, the particles are dissolved in some solvent, which in most cases is water. So let's say we have this container and we have this other container, and both both containers have I mean, now the particles are dissolved in water. So the particles are close together, the particles are far apart. This one is dilute, this one is more concentrated. So gases and solutions. But it doesn't apply to solids and liquids. Why not solids and liquids? Because in solids and liquids, the spacing never changes. So the spacing between the particles, it never changes. I mean, over here, the particles can be far apart, they can be close together in gases, they can be far apart, they can be close together in solutions. But the spacing between the particles never changes. तो अगर आपके पास कोई solid है ना, the particles are always tightly packed. तो ये हमारे पास, let's say we've got a solid, and you can see that the particles are always close together. अगर वो ज़्यादा भी बन जाए, here's another solid, the particles are still close together. So the concentration is fixed. I mean, they're always close together. They're always tightly packed. So spacing does not change for solids as well as liquids. Liquids may be इसी तरह होता है. The particles which are loosely packed, I mean, the kind of solids and liquids almost have the same spacing, and the spacing never changes. मतलब एक glass पानी होगा, उसको कहीं पे भी डाल दो, वो एक glass पानी रहेगा. Its spacing never changes. It doesn't expand. The particles don't become far apart or close together. So is this point clear? But, and remember, this is a very minor fine point, which a lot of people get a lot of questions wrong because of that. Okay, because remember this particular statement is only for concentration. When you change concentration, a lot of people by mistake think, okay, like if you increase concentration or you decrease concentration, the equilibrium does the opposite. I mean, for example, I've got a reaction, and that reaction is a reversible reaction. So, for example, if अच्छा, so here's an example. Got water, which is liquid in equilibrium with H2 and O2, which are gases. Let's say they are in equilibrium somehow. Okay, let's say it's a made-up equilibrium. The first thing is, if I increase O2, I mean, that's point number one. What will happen if I increase the amount of oxygen? Now, oxygen is a gas. So remember this statement over here, it specifically applies to, kahan pe likha tha, okay, it does not apply to solids and I think I wrote that. I think I should write. Well, where did I write concentration? I mean, this thing. This is the part where I wrote down concentration only applies to aqueous solutions or gases. So when I talk about increasing oxygen, the concentration will increase, obviously. Like if I increase the oxygen, if I have a gas and in the container I add more gas, the concentration of the gas is going to increase. So if I increase O2, its concentration would increase. The equilibrium would try to do the opposite. Equilibrium will favor that reaction which does exactly the opposite. So it's going to favor that reaction that does the opposite, that decreases O2. And that is going to be the reverse reaction. So that O2 gets used up, or that O2 gets converted into H2O. So equilibrium would try to do the opposite. It will try to it will favor the backward reaction. And tries to decrease the amount of oxygen. So that is the principle. You try to increase O2, equilibrium tries to do the opposite, favors the backward reaction, and tries to do exactly the opposite. But the forward kind of the amount of O2 would increase as well. So you don't want to do that. You're trying to increase O2, it's going to do the exact opposite. But if for the same reaction, for the same exact reaction, they start talking about water. Like what happens if you decrease water, you decrease the amount of water? Nothing would happen. Equilibrium would remain unaffected because the concentration never changes. For liquids, the concentration is a constant and it never changes. So you have to be careful about that because this particular statement, you increase something or you decrease something, the equilibrium tries to do the opposite. It only applies to concentration, and concentration is a term that is constant for solids and liquids. For them, concentration is always taken as a constant because the spacing never changes. Spacing only changes for gases or for aqueous solutions. ये clear है सारों को? बाकियों को clear? Oswa, is this clear? Amna, Reed, Aisha, is this clear? Clear है कि नहीं?
Clear, sir.
अच्छा, बाकी एक और चीज है कि जो आखिरी point है, we'll then practice questions. ठीक है, past paper questions on this. Another important. I'll just first summarize all of this that we wrote down. Okay, so that we know the Lee-Shatler principle. So I'll just summarize everything. So Lee-Shatler principle is before we move towards past papers on this. So Lee-Shatler principle is that the equilibrium tries to oppose any change that's introduced. It tries to do the opposite. Tries to oppose any change that is introduced. That is introduced. That's and the summary is you increase temperature, it's going to favor the endothermic reaction. I'll just write endo. You decrease temperature, it will favor the exothermic reaction. You increase pressure, which means कि आप compress कर रहे हो, it will decrease volume and produce less gas, or favors the less gas mole side. You decrease pressure, it will favor decrease pressure, you're expanding, so more gas would be produced, so favors more gas moles. और आखिरी जो summary है वो ये कि about concentration. You increase concentration, of anything. The equilibrium tries to do the opposite. It's going to try and decrease concentration, and obviously vice versa. So it's going to do the opposite. So those are all your rules for equilibrium. For this one, I told you that this particular rule only applies for gases because only they are compressible. I mean, pressure will have absolutely no effect on a solid or a liquid. You increase pressure, you decrease pressure. For a solid, nothing happens. And similarly for concentration, the term concentration only applies to gases or to things that are part of a solution. They're dissolved in a particular solvent. So that's your entire summary. Now, one very important point is that never confuse equilibrium with, and that's a very important point, never confuse equilibrium with rate. Now that's a very, very important point. What that point basically states is that, rate is something totally different. When you think of rate, rate is speed of reaction. So when you think of rate, when you increase temperature or pressure, this pressure thing only works for gases. What else? You increase temperature, pressure. So now similarly, you increase concentration, surface area, catalyst, or catalyst. there were 5 factors that affect a rate of reaction. So whenever you increase the temperature, pressure, surface area, catalyst, the rate goes up. Rate increases, and also vice versa. The rate would slow down. So this is something that you studied in O levels. Now, you have to be very sure, is the question on equilibrium or is it on rate? Because a lot of times they mix the two things up. Now, when you talk about equilibrium, like we've been talking about equilibrium for a while now. So whenever you talk about equilibrium, you're not talking about the rate of the reaction. When I talk about one reaction being favored compared to the other ones, or one reaction speeding up compared to the other one. So you got two reactions. One of them is the forward reaction. And let's say this is X turning into Y. So when I say that changing a certain condition and I say that X forward reaction is favored, if I write this statement, okay, let's say we apply the equilibrium and we apply Shatler principle and we figure out that the forward reaction is favored. Now that in no way is a statement about the rate of the reaction. It does not tell you about the speed of the reaction. What it only tells you is that the forward, so whenever we say that the equilibrium position shifts to the right or the forward reaction is favored, what that means is that the forward is faster compared to the backward reaction. So it's a relative comparison. What that means is that the forward is happening at a faster rate compared to the backward one. The backward one has slowed down. Now, in reality, maybe both reactions are slowing down, but one of the reactions is faster. The forward reaction is faster compared to the backward one. Maybe both of them are speeding up, but the forward reaction is faster compared to the backward one. Or maybe the forward reaction is still at the same pace. The backward is slowing down. So the forward becomes faster compared to, so it's a relative comparison. It's not a comment on the rate of the reaction or the actual rate of the reaction. It's the relative comparison. Maybe both of them are slowing down, but the forward is faster compared to the backward reaction. Or maybe both of them are speeding up, but the forward is still faster compared to the backward reaction. Or the third option is that maybe the forward has the same speed. It's the backward that's slowing down. So the forward is still relatively faster compared to the backward one. So is this point clear that equilibrium or this statement forward reaction or backward reaction is favored? It's not a comment on the actual speed of the reaction. Is this clear? You clear?
Yes, sir.
So remember this point is very important, that forward reaction favored, it's just a relative comparison. So make sure because a lot of times they do this. So make sure, be very careful. Is the question on equilibrium or is it on rate? You got to understand. You got to understand the difference. Now, another thing about this whole and again stressing this point, they'll very quickly switch. I mean, they'll be talking about equilibrium, and all of a sudden they'll be talking about rate. So when they talk about rate, don't think of this whether forward is favored or backward is favored. You increase temperature, no matter what the reaction is, it's going to speed up. You increase pressure, if gases are involved, no matter what the reaction is, it will speed up. Forget forward and backward. If they talk about equilibrium, then that means they're not talking about rate. When they talk about equilibrium, they're basically talking about the relative comparison. Now, another point is, why do we learn the Shatler principle? What's the point behind that? The point is, we need to increase yield. So there would be lots of questions. Yield means output. Basically, every time when we apply equilibrium, we want to do two things. We want to favor the forward reaction. We want the products to be formed. So we want the forward reaction to be favored. That's the first basic thing. In any reaction, we want the products to be formed. So we want more forward reaction. And we also want a faster reaction. So there are a few limitations. So we want more forward reaction, and we also want a faster reaction. There are two things that we want. Now, a few things that you should understand is that there would be some practical limitations. And they're going to talk about those practical limitations a lot. So the practical limitations is you can't have a very high pressure. That's the first one. That is going to be too expensive. TK, you did a lot of this stuff in O-levels. TK will practice a few more questions this time. So you can't have a very high pressure. That's just too expensive. Even though the Shatler principle would agree with that, but there's a practical limitation. I would like to have a 1 million atmosphere pressure, but that's kind of, you'll probably get that pressure on Jupiter or some other planet. So you have these practical limitations, and you can't have a very low temperature. At very low temperature, like even though the Lee-Shatler principle might agree with that, but the problem with a very low temperature is it would be too slow. Reactions will not have enough kinetic energy and they would be too slow. So two practical limitations, always be mindful of those. Can't use a very high pressure. Secondly, can't use a very low temperature as well. So we'll start practicing questions a bit. Just 1 second, let me open. So let's try and do. Let's try and do this one first. As I'll pick the easy ones first. So let's try and do, I'll only touch those parts which are related to the Shatler principle. So the first statement, increasing the pressure increases the equilibrium yield. So higher pressure, what's the rule? The rule is whenever you increase pressure, less gas mole side is going to be favored. So when you increase pressure, you're compressing. So less gas moles are going to be produced. So the forward side has 2 moles of gas. The backward side has a total of 3 moles. So less gas mole side, which is the less gas mole side? That's the forward side. So that's our forward side. So higher pressure, less gas mole side. So the amount of SO3 is going to be favored. There's going to be more forward. There's going to be more forward reaction. So the yield of SO3 will increase. Okay, is this clear? This first one. You clear?
Yes, sir.
So then Which statement about reversible? An increase in concentration of a reactant always increases the concentration of the product. So you got reactants, there's a reversible reaction, you got products. So when you increase concentration of a reactant, so remember, आप increase कर रहे हो, what would the equilibrium do? You're increasing it, the equilibrium will try to decrease it. So if you increase the concentration of the reactant, the equilibrium is going to try and decrease it. So it's going to make more products. So it's going to do the opposite. It's going to try and do the opposite. So if you're trying to increase the reactants, it's going to try and decrease that. So it's going to favor more forward reaction and there's going to be more products. So the first statement is correct, that if you try to increase it, increase reactants, equilibrium is going to stop you doing that by favoring the forward reaction. Okay, there's less reactants. I say an increase in temperature always increases the rate at which the equilibrium is established. Now, all of a sudden, they've brought in rate. Remember this. So it's no longer a question on equilibrium. It's basically the rate at which the equilibrium. So this question has nothing to do with equilibrium. So all of a sudden, the question has now switched to rate. Rate के बारे में क्या पढ़ा था कि जब भी temperature, whenever you increase temperature, the rate would increase. So that statement is correct. And all rates would increase, whether it's the forward or the backward. Whenever you increase temperature, the rate would always go up. Up last, an increase in temperature always increases the concentration of the product. That is not going to be true. Why? Because now again, he switched to equilibrium. He's talking about the product, amount of product at equilibrium. So when you increase temperature, the endothermic reaction is favored. So we don't know which one is the endothermic, and the endothermic reaction varies from one reaction to the other reaction. So it's not always going to be the product side that's going to be favored, because we don't know at the moment which one is the endothermic reaction. So which is why the third statement cannot always be correct. अच्छा फिर let's just focus on the easy ones first. We'll get a simple Shatler principle first. This is this one. So this question states that if the temperature of an equilibrium mixture of the gases is increased, so he's increasing temperature. So if temperature is increased temperature favors the endothermic reaction. So the delta H is always given for the forward reaction. It's got a positive value. That means the forward reaction is the one that's endothermic. The backward is the one that's exothermic. So if the temperature of an equilibrium mixture of the gases is increased, what will happen to the volume of the mixture? Increase or decrease, and why? So if you favor the endothermic reaction, which is the forward, because you're increasing temperature, the amount of gas would increase. 1 mole on this side. Now you've got 2 moles. The volume बढ़ जाएगा कि आपके पास you've got more moles of gas. So the volume of the mixture will increase or decrease. It will increase because there's going to be more moles of gas. So the volume will increase. So it's either A or it's B. So why will the volume increase? Because there's a shift of the equilibrium towards the right. That makes sense. There's a shift to the right. Second statement says the volume will increase because there's a shift of equilibrium towards the right. So यहाँ तक तो दोनों ही statements true है. The second statement is more true because it also states that there would be thermal expansion. So जब भी आप temperature बढ़ाते हो, what happens to gases? They expand as well. So there are 2 reasons why the volume would increase. One of them is that the forward reaction is being favored and there's more gas being produced. And the second reason is that at a higher temperature, gases expand. So there's thermal expansion as well at higher temperature. So B is a much better and more complete statement compared to A. Is this clear?
Yes, sir.
चलिए फिर यहाँ से ना let's continue. We'll do more questions. We'll do the difficult ones as well. Unleash Shatler Principle. ठीक है first. Say okay everyone. Take care. Allah Hafiz.
Allah Hafiz.